Okay, let's unpack this. Imagine a neural network, trying to learn a new skill. Could be anything. Recognizing images, writing text, playing a game. How does it actually get better at it? Well, the engine driving almost all of that learning is this process called gradient descent.
Right.
Think of it like trying to find the absolute lowest point in a huge foggy valley. You can't see the whole thing, so you just take small steps, always going downhill, feeling for the steepest slope nearby, and you adjust step by step until hopefully you hit the bottom.
That's a great analogy, and that's essentially what neural networks do, right? They tweak their internal settings, the parameters, constantly trying to minimize errors, get closer to the right answer. But what's really fascinating in the paper we're diving into today is how they take this fundamental idea, gradient descent, and sort of flip it on its head.
Flip it how?
Well, instead of just using gradient descent like an external tool to train the network, they're exploring how to make the network learn to do the optimization itself, like inside its own architecture.
Whoa, okay, so not trained by optimization, but the network becomes the optimizer.
Exactly. It's
Right.
optimizing itself from within. It's almost like its own internal learning algorithm. And they call this pretty groundbreaking concept in-context gradient descent, or ICGD.
That's a huge shift in thinking, isn't it? Just fundamentally
Right.
different. So our mission today is to really explore these incredibly clever and, yeah, let's be honest, quite academic innovations that allow a specific type of model, a transformer, to basically become its own gradient descent optimizer.
Mm-hmm.
We're going to pull back the curtain on how these things are designed, what, surprising new parts they actually need, and importantly, the rigorous math, the proofs that show this audacious idea actually works.
Yeah, the proofs are key.
So if you've ever wondered about the cutting edge of neural network architecture, what future AI might even be capable of, well, you're about to get a unique shortcut to understanding some seriously deep theoretical work. Okay, so many of you listening are probably familiar with in-context learning, right? ICL.
Sure, yeah. It's pretty common now.
That's the magic we see in, large language models, where they learn from examples you give them right in the prompt. No retraining needed. It's like showing a student a few solved math problems right before a test, and they just pick up the pattern and apply it.
Right. They generalize from the context.
But this deep dive, it pushes that idea way further. With in-context gradient descent, it's not just learning from the context, it's learning how to optimize within that context.
Ah, okay. So it's actively adjusting itself.
Exactly. Adjusting its own internal stuff to minimize some loss function, all happening inside, no external nudging. It's like that student not just solving the problem, but figuring out how to study better while taking the test.
That's a really interesting way to put it. And connecting this to the bigger picture, the main goal of this paper is really to build a specific transformer model. They call it NN theta. And this NN theta, given some starting input, let's call it H0, is designed to approximate, quite precisely, L steps of gradient descent internally.
So it mimics the whole iterative optimization process inside itself.
Precisely. And this NN theta isn't just any old transformer. It's specifically built for what are called N-layer feed-forward networks. And it borrows ideas from both ReLU transformers and Softmax transformers, trying to get the best of both worlds.
Okay, and you mentioned the scale.
Right. The scale is kind of mind-boggling. This internal optimizer network, NN theta, it actually has 2n+4l hidden layers.
Yeah, that's a lot of layers.
It is. It shows you the complexity needed to simulate optimization internally. And breaking it down even more, each single step of gradient descent within that whole process isn't just one layer either. It's approximated by this complex neural network block. And that block itself has 3 parts in sequence.
Okay, what are they?
First, the transformer layer they call TF theta n+2.
Yeah.
Then a really crucial layer, EWML thetan. We definitely need to talk more about that one.
EWML, okay.
And finally, another transformer layer, TF theta 2. It's this whole intricate setup that lets the network process and update its own sort of internal weights as if it were doing gradient descent.
That complexity alone really hints at the challenge here. And that brings us neatly to the first big innovation, which I found really insightful. You might think, okay, standard transformers, they have attention, they have MLPs, they seem so powerful. They can translate, write code.
Mm-hmm.
Surely they can do basic math, right? Like multiplication.
You'd think so. But the paper points out this fundamental, almost surprising blind spot. Typical attention mechanisms and MLPs, they actually struggle with something that sounds simple.
Yeah.
Element-wise multiplication, or what they call self-products.
Element-wise multiplication, like just multiplying x and y if the input is xy.
Exactly that. It seems trivial, but standard transformer blocks just aren't built to do that efficiently or naturally. And think about it, for a network to do gradient descent, especially backpropagation, it has to multiply things. Activations by weights, error signals back through layers, multiplication is everywhere.
Right. Backprop is full of it.
So, if your basic building blocks can't easily multiply corresponding elements from two vectors, how can you possibly implement gradient descent internally? It's like having, a supercalculator that can do calculus but stalls on 2 times 3.
So that's a huge hurdle.
Yeah.
How did they get around it? How do you build that multiplication capability into the transformer?
This is where their first really clever innovation comes in. They introduce a totally new architectural component, the element-wise multiplication layer, or ELML.
A new layer type.
Yes, not just tweaking existing ones. And alongside it, they define the specific mathematical operator they call gamma, go. This gamma function is pretty neat. You give it a square matrix, and it zeroes out everything except the numbers on the main diagonal. It keeps those, sets the rest to 0.
Huh. How does that help with multiplication?
Well, by carefully structuring the inputs and using this gamma operator within the ELML layer, they can effectively isolate and perform the needed element-wise products that standard layers fumble. And they state this very clearly in the paper in Remark 3. They say without this ELML, it's basically impossible for transformer layers to achieve our goal without any other assumptions.
Wow. So it's absolutely essential.
Absolutely vital. It's the key to implementing those backpropagation calculations inside the ICGD process. Things like calculating specific gradient components, PJ they call them, rely fundamentally on these multiplications. It's foundational for the whole proof.
That is genuinely elegant, building the missing calculator right into the architecture. Okay, so they've got the multiplication sorted. But gradient descent needs to be pretty accurate, right? How do they make sure these internal calculations are precise enough?
Excellent point. Precision is critical. And that leads us straight to their second major innovation. This one is about ensuring they can provably approximate complex functions accurately, and it ties back to a seemingly small detail, but one with big consequences. Their choice of activation function.
Activation function.
Yeah. The paper explicitly mentions using a normalized ReLU activation. They write it as Sigmin, not the standard ReLU, and significantly not the more common Softmax for certain parts.
Normalized ReLU Sigmin. Why the normalization? What's the N doing there?
Good question. The normalization dividing by n is key for keeping things stable. It ensures the outputs of the activation function stay within a predictable bounded range, which is super important when you're stacking these things up in, hundreds of layers, like in their n and theta, and using them repeatedly to approximate math operations for ICGD. Things can blow up otherwise.
Okay, stability. But what about the ReLU part itself? Why ReLU for approximation?
That's where a core theoretical result, lemma 7 in their paper, comes in. This lemma rigorously shows that ReLU functions, especially these normalized ones, can provably approximate smooth k-variable functions.
Smooth functions, meaning functions without sharp corners or jumps.
Exactly. And crucially, they can approximate them to any desired degree of precision.
Okay, so if I'm following, the network needs to be able to represent these smooth functions accurately inside itself, because gradient calculations depend on the shapes of these functions.
You've got it. Think about calculating a derivative that's the slope of a function. If your network can't accurately represent the function itself, it can't possibly get the slope, the gradient, right? The proof they sketch out for this approximation ability is quite interesting. It's a 3-step process.
How does it work?
First, they approximate the target smooth function using piecewise constant functions. Imagine like a staircase, flat steps. Second, they use ReLU to turn those flat steps into connected straight lines, piecewise linear approximations, much closer to the smooth curve. This step also helps sort of discretize or quantize the input range, making it easier to handle.
Right, breaking it down.
And finally, they use standard feed-forward networks to actually predict the output values based on these linear pieces. And they carefully analyze the error, showing it can be made arbitrarily small. They even provide specific constants and parameters, epsilon, outapprox, R, H, C, that guarantee the accuracy. And they note if you need even more precision, you just need finer steps in your approximation.
So it's a really rigorous way to ensure the internal math for the gradients is actually trustworthy.
Exactly. It ensures the internal gradient calculations are accurate enough to genuinely mimic true gradient descent.
Okay, so we have the multiplication handled by the ELML. We have accurate function approximation using normalized ReLU. But there's another piece, right? If the model is processing multiple examples or tasks in its context, how does it keep track? How does it know which gradient calculation belongs to which input sequence?
That is a critical point. If everything gets jumbled together, the optimization won't work for individual examples. It has to keep things separate.
Which brings us to token-wise separateness and contextual mapping. Sounds technical.
They are a bit, but the idea is crucial. Imagine you feed the model several different problems in its prompt. It needs to work on each one without confusing them. So, definition 12 in the paper formally describes token-wise separateness. It's basically a set of mathematical conditions ensuring that the representations of different input sequences or tokens stay far enough apart in the model's internal space. They use parameters like armin, armax, delta to guarantee this distinctness.
Okay, so making sure inputs don't blur together.
Right. And building on that, definition 13 introduces contextual mapping. This is essentially a function whose job is to assign a unique ID, like a tag, to each distinct input sequence within the context.
Like putting a unique sticky note on each problem it's working on internally. But how does a transformer do that? Isn't attention usually about finding relationships between tokens, not separating them with unique IDs?
Ah, that's the really clever part. They rely on another result, lemma 17, which they cite from a 2024 paper by Kajitsuka and Sato. This lemma proves quite rigorously that a specific type of attention block, a Softmax-based one-layer attention block with certain properties, can actually function as this contextual mapping.
So the attention mechanism itself can be used to assign these unique IDs.
Precisely. It's not just about relating tokens. It can be engineered to identify and separate distinct input contexts. This is absolutely essential for the in-context calculations to be accurate for each specific input. And it's important because, as we discussed with ReLU, the inputs might get slightly changed or quantized during the approximation process.
Right.
This contextual mapping ensures that even with those small changes, the distinct inputs remain separable. The model always knows which calculation belongs to which original input context. It prevents everything from becoming a confusing mess.
Okay, that ties it together nicely. So you have these three core innovations working in concert. The ELML for multiplication, the normalized ReLU for accurate approximation, and the attention-based contextual mapping for keeping input straight. When you put all that clever academic machinery together, what's the big payoff? What's the main theoretical punchline?
The payoff is the paper's main theoretical result. This is Theorem 1, and they also have a more generalized version, Theorem 4. These theorems are really the foundation supporting their entire claim.
And what does Theorem 1 actually state? What's the big news?
Theorem 1 delivers a pretty monumental statement. It says that if you meet certain conditions, basically, the functions involved need to be smooth enough, and the inputs and parameters have to stay within certain bounds.
Okay, under those conditions.
Then there exists a transformer model, specifically their N and theta model, with that exact 2n plus 4L layer structure we talked about. And this model can implement L steps of in-context gradient descent on N-layer neural networks.
So it's not just maybe it works. They've mathematically proven that such a transformer can be built.
Exactly. It's a proof of existence. They've shown it's theoretically possible to construct this internal optimizer. The proof sketch goes into detail about how specific layers are designed for each GD step and how they carefully track and bound the errors that accumulate.
Accumulating errors sounds potentially bad, though.
It can be. They acknowledge that in the general case, errors could grow exponentially over many steps. But crucially, another result, lemma 14, clarifies that their framework also provides conditions under which this approximating GD does converge.
So they show how to control the precision too.
Right. It means they've not only shown it's possible, but they've also mapped out the conditions needed for it to work reliably. Essentially, this special N and theta network can follow the true path of gradient descent closely enough. It learns to find that optimal path using its own internal layers, rather than needing an external algorithm to guide it.
It becomes a closed-loop optimization system, all inside the model. Wow. Okay, so today, we've really taken a deep dive into some genuinely academic, very innovative stuff in neural network design. We looked at the need for custom layers, like that element-wise multiplication layer, to handle basic math that standard transformers surprisingly struggle with. We saw how crucial normalized ReLU is for getting provably accurate approximations of the complex functions needed for gradients.
Yeah, the approximation theory is key.
And we uncovered that clever use of attention, not just for relating things, but for identifying different contexts, keeping everything straight internally with contextual mapping. This paper really paints a picture of neural networks moving beyond just doing tasks to actually learning the process of learning, the optimization itself from within.
It It really does. And it leaves us with a pretty profound question for you, the listener, to think about. If we can design neural networks that intrinsically learn and perform optimization, like gradient descent, right inside their own workings and context, what does that really mean for the future of AI? For how AI learns and adapts?
Could we start seeing models that become much more autonomous in how they learn, maybe adapting their own optimization strategies on the fly without us needing to intervene or do massive retraining cycles? What kinds of new breakthroughs could this unlock? And what fundamental limits about AI learning might this push against? The implications, well, they feel pretty vast.